Hi, so thank you guys, thank you for being here and listening to my talk. Uh, yeah, if you are going to finish this. So, my talk is about classifying search queries using no user click data. So we have user logs, and what I'm going to show you uses no user logs. So let me first introduce myself. So I'm currently working in the data science team at Searchmetrics. I like playing with data a lot, making data-driven studies, and I like AutoML. Without looking at data, you can apply a lot of machine learning models and come to build like a really good model without even looking at the data. And I'm very much interested in applied ML. So in this talk, we'll see how search queries can be classified without using any user logs or user click data. And this talk is more oriented towards applied ML rather than mathematical formulas. So don't expect any kind of mathematics in my talk. I won't explain what neural networks are, go into details of neural networks or LSTMs, but rather than I'll tell you how to use them properly. And I think that's what we are looking for. So let's start with the data Searchmetrics, the company I'm working for. We have quite a lot of data. And when I say a lot of data, yeah, we have petabytes of data, like every day. And it's growing every day. So with over 800 million search queries and new queries being added every day, hundreds of thousands of new queries are being added every day, we need something, we need a system which classifies these search queries into categories. But why? Why do we need that? Because, yeah, okay, my manager came to me and told me, yeah, okay, classify search queries. No, it's not like that. So, yeah, for every day we use Python, scikit-learn, Keras, which is a neural network library for Python, and XGBoost, the gradient boosting library. So let's look at search queries. So many of you, I think, you have come from outside Berlin, and yeah, you looked at the weather in Germany, in Berlin, and you were very happy. It's 23 degrees. On the weekends, it's going to be 29 degrees. Yeah, so yeah, let's search for things to do in Berlin. And then Google shows you this. Okay, yeah, go to Brandenburg Gate, go to Museum Island. Don't go inside Museum Island, it takes a lot of time. And go to Checkpoint Charlie or something. And it shows you a knowledge graph. It gives you, okay, how much do hotels cost, a 3-star hotel or average 5-star hotel, how much do they cost? You can click on the links, you can book hotels, and you don't even bother to click on the Google search results. Why should you? You're getting all the information. Similarly, when we look for something like PyData or child labor laws, so if we are looking for PyData, we get the website of PyData. We're looking for child labor laws, we get an information graph directly from Wikipedia, and okay, maybe that's what you are looking for until unless you're going to details of child labor laws. So this is one more example. So I'm a gadget junkie. I think many of you are. So I like to search for new gadgets online. So like S7 Edge. So Google gives me 4 different advertisements, and then I can click on any of the link. And if I want to buy something, I just click on the link, go there on their website, and buy stuff. So why classify such queries? For businesses, right? Any business, if it's a small business, like a very new startup company here which is selling electronic stuff, let's say, or furnitures, or a very big company like Amazon, they all want to find out what the user intent is when the user is visiting their website. They can log it from Google Analytics, and they know what queries were used and how the users came to their website. So they also want to know which queries are important for them so that they can optimize their content accordingly. But for data scientists, hundreds of millions of unlabeled keywords to play with, so why not? I'll do it. So when we are talking about keyword classification, we must also know what the different classes of keywords we are talking about. So we have navigational keywords in which the user knows where he wants to go. So if your search query is Amazon, let's say, so you already know you want to go to Amazon website. You don't want to buy Amazon. So it's like kind of a navigational query. And then we have informational queries. Okay, so if you're looking for how to tie a tie, it's more of an informational query. And so it gives you a lot of information. Google has a lot of knowledge graphs that it shows to you when you look for informational queries. Then you have very important for industries, transactional, oh, fuck. Sorry. Oh, okay, thank you very much. Sorry about that. Okay, yeah. Yeah, for businesses, then data scientists, crying guy, tears of joy. So then we have transactional queries, and these queries represent intention of buying a product or a service. So if you're looking for a Galaxy phone or iPhone or whatever phone, or you're looking for shoes, clothes, or you're looking for a plumber to fix something in your house. So these kind of queries are transactional queries, and so after that, you already saw that, so it's no surprise anymore. Is that it? No, it's not. So for transactional queries, they can be further divided into 5 more categories. So I'm explaining these categories because I want to go deep into data and the machine learning models, and before that, you should know. So how many categories do we have? So we have transactional, and inside transactional, we have awareness phase or research phase. User wants to purchase something, then it comes into purchase phase. Or if you have an iPhone, and a lot of people want to fix their iPhone all the time, so that's the retention phase. And then we have other categories, you know, like geography, science, health, people, a brand, and millions of other categories. So where do these categories come from? They come from Wikipedia. Wikipedia has more than 1 million categories right now. So what was the traditional way of classifying these queries? So based on rules. Everything was based on rules, and they needed user search logs. So you're looking for something, and okay, you didn't like the query, you didn't like the results, you come back, and these search logs are analyzed by these researchers that I have mentioned here at the bottom. So you can check out this paper. It's a very nice paper. And then you have, they classify into 3 categories: transactional, navigational, and informational. So if you have a query length less than 3, then it's classified navigational. If it's more than 2 and it's not navigational or transactional, then it's more of an informational query. If you're looking for a movie, song, then it becomes a transactional query, or image or video collection. And there are, in information queries, we have question words. So when did this happen? Who is the president of the United States? Something like this. So these are more of informational queries. So now let's look into classifying without search logs. So what do we need? Of course, we need the search query because we want to classify the search query in some category, right? And we need some knowledge about the word-to-vec embeddings. We need info about the top search results that come with a query, some SERP integration. So SERP is search engine result page. So what kind of integrations you see? You see a knowledge graph, you see some information. If you search for Berlin, you see some information about Berlin. It's the capital of Germany or something like this. And you need some knowledge about what unsupervised learning is, some rule-based labeling that we already saw in the previous slide. Of course, maybe at some point you need mechanical Turks. So if you labeled your data incorrectly, maybe they can fix them for you for some money. And yeah, you need to know about the machine learning models. So today I'm going to talk about 3 different machine learning models that I used here to classify these search queries. So the first of all, we look at the word-to-vec in search queries. So we all know about word-to-vectors. So every word can be represented in multiple dimensions. So we use 200 dimensions, and Germany can be represented by a vector, Berlin can be represented by a vector. So when you have different words and they are being represented by vectors, if you subtract the vector of Germany from Berlin and you add France to it, it becomes very close to Paris. We all know that. We have seen these kind of slides a million times, but what happens with search queries? So with Google now or Siri, you guys are looking for something like this. So what's the weather going to be in Berlin? Or weather forecast of Berlin? And what do you get? You get your weather service for Germany. You don't get things about going to Berlin or about Shakespeare in Berlin. And I think Google is changing now. So if you're looking for queries like this, it understands what you're exactly looking for and gives you appropriate results. So these are some of the real search queries. And I think these are real search queries, so viewer's discretion is advised. So you have like funny pictures and Bing images very close to each other. Then we increase, and then we see like, oh yeah, Craigslist somewhere. We have Google Flights. So as I keep on adding more queries to it, so Craigslist forms a cluster there. So and then there is a cluster of dating websites here. So like Adult Friend Finder or Ashley Madison. We have Bank of America, some bank loans stuff. At the same location, we have Capital One credit card, Lowe's credit card. So these search queries from a cluster, and this has, we took word-to-vec representation for each word in the search query and normalized them according to the number of times they appear in the search query. Every word appears in the search query, and they have been decomposed using TSNE and represented here. So there are two approaches that we use for classification. So you have, the first approach is a combination of boosting and convolutional neural nets, which classifies queries into navigational, informational, transactional, and the buying cycles. The next one is LSTMs, which are used to classify keywords into more than 30,000 categories. So for the first approach, we need a feature extractor. Of course, we need a lot of features if you want to build a good model. And you need to label the data. We need a SERP extractor. So you need the search engine result page. And for the next one, you need the Wikipedia categories, because if you want to classify into Wikipedia categories, of course, you should know about Wikipedia categories. Then we have like the top search results from the Google page, and you calculate a word-to-vec score. You combine them together, calculate a cosine similarity or something like that, then see how close they are. And then what we use is refining of categories with knowledge base. We have an in-house knowledge base, and you can you can learn more about it tomorrow. And then we use a LSTM and classify in over 30,000 categories. So let's look at the second pipeline first. So word-to-vec and LSTMs. We have you cannot classify. You can, but it won't be good in 1 million categories. So you need to boil down to something like 10,000, 500, 10,000, and you keep on increasing unless you get good results and your results don't go bad. So we took like 30,000 categories and 1 million search queries. We mapped each and every query to a word-to-vec space, and every category from Wikipedia to word-to-vec space. And then we and then we found out, okay, if you search for something, there are like 10 websites appearing. So we calculated word-to-vec for each of their titles after some cleaning. So we removed the search query from the title, and then we calculated this word-to-vec space for each one of them. Then we extracted top categories using the cosine similarity, and we used this label data for our LSTMs. So you can use LSTMs in a number of ways. So if the search query is something like the White House, of course, the won't be represented by a word to vec, but I'm just showing it here. So every word in the search query can be represented by a vector. And these vectors form a sequence for the sequence-to-sequence learning of LSTM. And with Python, it's so easy. If you're using Keras, if you know about Keras, it's so easy. You just need 10 lines of code to implement this LSTM. And this is a very big LSTM network. It takes a lot of time to train. So in the first, you have like 3 LSTMs here. First one has 512 nodes, 128 nodes, then 64 nodes. The first 2 are returning sequences. The last one is not. Then you have a sigmoid layer because a keyword can belong to many categories. And when you train a network like this, we obtain some results like these for this query. So like, yeah, White House, United States, president, politician, yeah, everyone is happy. Okay, yeah, pretty good. So now let's look at the performance of the network. So we see that the training loss here is multi-class log loss. It goes down, and it keeps on going down. The validation accuracy keeps on increasing from somewhere around 59% to 62%. It keeps on increasing if you keep on training for more epochs. But we saw that LSTMs are very slow to train. For one epoch, it takes like, for a million samples and one epoch, it takes like 2 hours to train on a GPU. So I think it's better to avoid it. And it was also observed, like when we are voting using a keyword knowledge base and Wikipedia categories, we do like 2 or 3 votings, and we include the Wikipedia text in that, then it performs much better than LSTMs. So why waste our time on LSTMs? And still, as I said before, it doesn't, so there were a number of categories before: navigation, transactional, or informational, and still it doesn't classify buying cycles and or user intent. And that's what we are looking for. So then we move to identifying the user intent. So let's go back to the example we saw first at 7edge. So what do you see here? Like 4 ads. There are like 8 product placements ads. So you just go on them, you click on them, buy stuff. Here, user is making himself aware of the product. It's definitely a transactional query because it's asking you for money. It's easy to label. You see these things, yeah, you can label it as transactional. Then we can use the number of ads that appear as features, the number of titles, the top titles as features. So when I say we are using top titles as features, it means it's a word-to-vec representation of the top titles. Similar example, PyData. So yeah, maybe people who don't know about PyData website, they Google PyData, and this comes up. Now, what we don't observe is this. We see there are a lot of navigational links. The user definitely wants to go to PyData website. He doesn't want to buy burgers. And yeah, so that classifies it as a navigational query. Barack Obama. We have a Wikipedia link, some news, some Twitter stuff, a knowledge graph. User doesn't want to buy Barack Obama. It's not transactional query. It's more of informational. He wants to know about Barack Obama. So we used all this info for initial labeling of data. As I said, hundreds of thousands of keywords every day. How would you label them first to train a machine learning model? So a lot of modifiers were used, a lot of rules, as explained earlier, and we added a lot of other rules in that. We used the search integrations like knowledge graph or information graph, but we didn't use mechanical Turks. So what I think, if we use mechanical Turks, the results are going to improve. So the queries are like navigational, transactional. Some navigational queries can be transactional. If you search for Samsung, maybe you want to buy a Samsung product, or you're going to the Samsung website. And of course, informational queries can also be transactional, and transactional queries are then further divided into awareness, evaluation, decision, or retention. So for these two different types of classification, we took only the transactional queries. For the second part, we took only the transactional queries, and for the first part, we took like 100,000 queries, and for the three main classes, which were already labeled according to the rules, modifiers, and search integrations. So if you look at this graph, if it's visible to you guys, then you can see like apartments, the queries related to apartments form a cluster. So these are word-to-vec embeddings, again. For buying cycles, since there were 4 classes, we took 100,000 queries each class. Next comes the interesting part, using convolutional neural networks. So yeah, when it comes to convolutional neural networks, we think about dogs or cats. Yeah, how can we distinguish between dogs and cats? We can represent search queries by images. So for every search queries, there exists millions of search results or hundreds of thousands of search results. We can take every title and convert it to a word-to-vec representation, stack them together, and it acts like an abstract image for that. So David Weir. So that's David Weir. He won't be happy if he sees this. So then we have like an image for apple juice or Irish. Yeah, okay, but yeah, a lot of you might think, yeah, it doesn't make sense. I don't see any difference here. Guild Wars or apple juice. Well, humans don't. Computers do. But even computers fail sometimes. So like this one. Is it a bug or a loaf of bread? So then we come to the machine learning part of it. We use 2 different kinds of model to separate queries into navigational, transactional, informational, and after that, awareness phase, the different buying cycles, the 4 different buying cycles. So for booster trees, I used word-to-vec embeddings, title from the top results that I got, additional features from the SERP pages, TF-IDF, so every search result was considered as a document, and TF-IDF was performed on it. And God bless the Yank Shen for writing XGBoost. It's the most awesome gradient boosting library I've ever seen. And it takes like, 10 lines of code to implement it in Python. Similarly, we have convolutional neural networks. So we can use images directly, feed it to the convolutional neural network, or we can randomly crop the images. So we can take a square image, we can crop them, we can add them together, we can use a lot of different pipelines. I'm not showing it here, and then we can pass it to the convolutional neural network. So how easy is it to implement a convolutional neural network with Keras? So here I'm showing a multi-layer perceptron. So you add a model, a sequential model, then a dense layer with 400 nodes, a rectifier linear unit, a dropout of 15%, and then you keep on repeating, or if you want a lot of layers, you keep on repeating that, then in the end you have softmax or sigmoid, depending on your data, if it's multi-label or multi-class. And similarly, you can implement a convolutional neural network. So here we had a very huge network with so we had a very huge network, with 2 convolutional layers, 1 activation layer between, then another activation layer, dropout. So I've shown only half of the convolutional neural network here because I don't want to discuss what exactly our network is. And then you have something like a softmax if you're, so there were 2 models, one to distinguish between navigational and transactional, one to distinguish between navigational and informational, and another one for transactional or not transactional. So some results. a user looks for buy Samsung Galaxy, and yeah, of course, yeah, our intuition says, yeah, it's a transactional query. Where does it belong? Yeah, if it's buy Samsung Galaxy, the user, maybe he's going to buy a Samsung Galaxy. So it's more of a decision phase. Similarly, if you're looking for Berlin, then it's more of an informational keyword with a location flag in it. Yeah, so there's also a location model, and I didn't talk about it. And if you're looking for Yahoo Mail, you want to go to Yahoo Mail web page, and it's more like informational, so 98% probability of it being a navigational keyword. And yeah, Oculus Rift, maybe you want information, maybe you want to go to the page of Oculus Rift because it's rather new. So yeah, here maybe you can say maybe it fails. But if I look at it, yeah, it doesn't fail. Yeah, it's navigational. If you search for Oculus Rift on Google, Google page, you get the navigational links. You don't get any product ads or something. And yeah, similarly, you have iPhone repair, which happens quite often. It's more of a transactional keyword, or maybe you want information about how to repair your iPhone. And it's in the retention phase, which is very difficult to distinguish from other phases. And PyData tickets, yeah. You want to make a decision, you want to go to PyData, you're looking for the tickets. It's a decision buying cycle, but yeah, the probabilities of the other classes are not so good here. So the conclusions, I came up with a very fast network for classifying search queries. So like more than 1 million queries can be labeled every hour. We don't need any user click data. We are still doing a lot of research on it. Model is improving day by day with addition of new keywords. It's outperforming the traditional methods in terms of data, in terms of accuracy. And we do have a paper in progress, and you will read more about it if you read scientific papers. And thank you very much.
Thank you. As usual, questions, please. One.
Hello, thanks for the talk. I want to ask, how do you deal with homonyms? Yeah, and what is actually representation of homonyms in Word2Vec?
Oh, there is no special treatment. So, no. We just train a Word2Vec model on the whole Wikipedia corpus, and it gives it.
If I search for the White House, if I search for White House, but I mean literally White Houses, not the White House.
Well, any model cannot go into your mind and see what you're thinking of at the time when you're looking for the search result. So when you're using LSTMs, of course, it can distinguish between White House or House White. But not these models, like convnets cannot. But we can distinguish them using the search results that come up. So if you're building this convolutional neural nets on the search results, building an image model, then yeah, it can distinguish.
Just a couple of questions regarding Word2Vec usage. How do you model like multi-words? You say you map a sentence as a query into a Word2Vec space. The second question is, what implementation did you use, and how do you validate the training? How do you know the model, the parameters you pick are good for that particular scenario?
The parameters for what?
For Word2Vec.
Okay, so we use GenSim for building Word2Vec models, and to combine, like, so every word can be represented as vectors. To combine these vectors together for a sentence, we are using some kind of normalized averaging. So if a word appears 2 times, the vectors multiply by 2 times. You can also take log averaging. You can multiply by the log of times they appear.
GenSim also has an implementation, I think it's no longer experimental, of something called Doc2Vec, which is an extension of the model.
Yeah, I've never used Doc2Vec.
So check it out. It helps also.
Yeah, sure, I will do that.
So you say you're learning these intentions without using user click data, but what you're using in fact is the result that Google gives, which are, as far as I know, learned user or built using user click data.
Yeah, but
So
I'm
it's
not.
not
So, yeah, of course. So Google modifies their search results based on the click-through rate. So if you like the website, which is at position number 20, and if a lot of people like it, then it's going to move up to 1 or 2. When I say user click data, I mean that, okay, you search for Samsung, then your cookie is being recorded by Google, and it's observing that you search for Samsung, then you search for Samsung Galaxy, then or you search for Samsung TV or something like that. So I'm not using this data as traditional methods do.
Do you have any plan? So you're only using Google data, are you? Do you have any plans to try it on a different data set or anything?
I'm sorry, I didn't get your question.
As in my question is, you're training the data set on the Google results. So
The training data set,
for example, if someone searches for Amazon, they're going to get Amazon website, not Amazon the rainforest, because Google brings up Amazon. Do you have any plans to try it on Google has a specific algorithm by which they give you the results. Do you have any plans to try it on a different data set which would return more specific results? Or?
Yeah, so we are working on a different search engines, but I haven't tried it yet. And as far as Google is concerned, if you look for Apple on Google, you get Apple Incorporated. But if you look for apples, you get the fruit. So yeah, I know it's a bit weird with Google, but we are using Google for now.
We still have more time for questions. Wait, you're pointing to somebody. Sorry.
Hi, great talk first. Just one question relating changes in Google results. So what happens if Google changes their top results? How often do you retrain your models?
Well, I don't care. If I've trained my model on 1 million keywords or 500 million keywords, I don't care anymore if Google changes or not.
But what happens if a new keyword comes up?
You tell me, what happens?
You need to read.
So Google has recently implemented something called RankBrain, which Google is using for like 10-15% of search queries, which are very, very new, which even Google hasn't seen before. So we believe RankBrain is something like expressing the search queries as thought vectors. And word2vec is not exactly thought vectors, and it's just a hypothesis. We cannot replicate Google. Maybe RankBrain is an ensemble of neural networks. We don't know. So we just keep trying, and maybe right now, this word2vec embeddings work a lot better than previous methods. So yeah, maybe we change that in future.
Thank you.
Thanks.
Do you detect term clusters? Like, for example, if I say software engineering, like treat it as just one term in your vector model, because software engineering is composed by software engineering, but if you see a lot of time together, probably it means semantically just one thing.
Oh yeah, so n-grams, right?
Yeah.
Yeah, so n-grams are used, yeah. So if software engineering appears once, so there is one vector for software engineering, not one for software engineering.
Anybody else? If this is not the case, I thank you very much, Abhishek. Now I got it. Thanks.
Thank you.